Linda, we can start.
Okay. He's ready?
Yeah, he's ready.
Okay. Okay. I think I'll be a bit faster because it's a little bit long. So in short, like when you're talking about ensemble learning, this is basically like you are taking many models. Like at some point maybe you are using one model and maybe you are not getting a good model performance. So you ensemble them so that you have multiple models, like you combine them so that you can try and achieve a higher overall model performance. So that is what ensemble method means. Like you're just combining a number of models, and at some point it can be either multiple versions of the same model, or sometimes you can decide to combine a different version of a version of different models together, so that maybe you can have an overall, like an improved performance or a higher performance, and like if you could have used the first one. So you can see they say the ensemble can consist of multiple models trained on the same data set. Each of these models is used to make predictions on the same input. Then these predictions are aggregated across all models in some way, for example, by taking a mean to produce the final output. So for example, you can take the models and you want to improve them. So if you combine them, you can either aggregate them to get like the mean, and then you produce the final output so that you can have a good overall model performance. So basically in ensemble learning, you have multiple models, and those multiple models, at some point they are called weak learners, which are trained to solve the same problem and combine to get better results. So as you can see here, I've just illustrated, like you can pick the first learner, which is weak, the second one, the third one, the fourth one, all the way, it can be all the way to n. So you combine them so that you can get a strong learner here, which is here. So the main principle here is you want to get a very strong learner so that you can increase the accuracy of the predictions that you are making. And the goal here for ensembling is because you want to reduce the variance, you want to reduce the bias, and also you want to make sure that the prediction that you are getting is improved if it was compared for you using a single model approach to do the prediction. So that is all about ensemble. That is all about ensemble learning. So I'll go ahead and just use the data that we are using yesterday, which is salary_data.csv. So you import the packages that are needed. You read the file, which is a CSV file, then you just check the head. So we have two columns, which is the year of experience and salary. You can go ahead and do some wrangling about your data by looking at the info, describe, just to get more information about your data. For example, if you look at the info, we can see we have 30 entries in our data. We don't have null values. Our data type is float. That means both years of experience and salary are integers. You can also look at the number of entries. We have 30 entries. At describe, you can look, we have counts which are 30, both for years and salary, the mean, the standard deviation, the quartiles, the median, and the maximum and the minimum value. Then I went ahead and to just check if you have any null values in your data frame, and you got to have no null values, and the data types, as I told you, they are float, and float is considered to be, is it an integer? No, not an integer, it's numerical, sorry guys. If it's numerical, float and integers are always numerical, so it's a numerical value, like if we could have gotten maybe an object. Yeah, so we'll go ahead and just build an individual model. And for building an individual model, you have to make sure that you are assigning your x variable, you are assigning your x, which is the independent variable, and you are assigning your y, which is the variable that you want to predict, which is the dependent variable. So for me, the years of experience are the independent variables, and the response variable is the salary. So you assign them. There's a person asking yesterday, you can decide to use the two brackets, or you go ahead and reshape, which is no problem. So I assign them so that I have my X and Y. Then you go ahead now to split your data into training and testing sets. So you go to X train, X test, Y test, and then you use now the sklearn model packages, which is train test split. So you split it on X and Y. Then the test size is 80-20%. So we are training on 80 and we are testing on 20%. Then the random step, which is equals to 42, is just for reproducibility of our data set. Then to build a model here, we were using a decision tree regressor, which we build yesterday, and we went through the decision tree, whereby we said it usually divides the data into sub-splits or subsets. Then after splitting the data, it always makes sure that after that it minimizes like the MSE so that it can get the better performance of the model, or the better prediction of the model. So you have to import the package decision tree regressor from the sklearn. Then also I wanted to check at the mean squared error, so I imported the mean squared error package from sklearn matrix. So for here, you have to initiate first your decision tree, which you can call it any variable. For me, I said it's a tree model is equals to now the decision tree regressor. Since you are instantiating it, then you're giving it a random set of 42 just to increase your reproducibility of your model. Then the max depth of 3, that means it will go 3 decisions, or it will do 3 splits in the data set that will give it the training data set. So when you run the model, you'll get the model is instantiated. So this is how it will look like. Then after that, now you come and predict now the value. Actually, after you've instantiated your model, make sure that you always remember to fit it. So you are fitting it on your training data set. So that is the X train data set. That is the X train, and the Y train. So that it can fit your model. Then after that, now you can make predictions. Like for here, you predict on the X test. Then you can carry out, calculate maybe the MSE or the RMSE if you want. So for me, I was getting my MSE here is 100 and is it 1,106? I don't know. It's 11,693,790 and something. So that was my MSE. And remember, the mean squared error is the one that it gives the difference between your actual target values and your predicted values made by the model. So in this context, for me, you can see we were predicting the salary based on years of experience. And you can see that the MSC that I'm getting is approximately 116,934,760. So this suggests that there's a little bit high MSC for this model, like for predicting salary based on years of experience. And in the case whereby you are getting a high MSC, this means that the model deviates substantially from the actual values in the data set. So this means it's not capturing well the underlying relationship between years of experience and maybe the salary that you are getting. And the reason for this is because maybe our model is overfitting, or it's undergoing, it's also underfitting, or maybe we don't have sufficient data to build this model. So that's why maybe our MSE is that high. So this means that as making predictions of salary from using a decision tree, from predicting the salary from using the years of experience, our MSE is very high. So that means there's some, it's not that much accurate. So we cannot rely on that. Yeah. I think from there, maybe I can stop. Then check if you people are okay. Or if I'm fast. Okay, thank you guys. Thank you so much. So from there, I think here I wrote a bad spelling. So from there now, we can go ahead now to see if we can build an ensemble method. And when it comes to ensemble method, you can realize that a random forest is always given as an example of that. And that's why here I used it just to showcase. So if you use a random regressor, you can do the same thing. The first thing you do is always make sure that you instantiate your model. So you instantiate and train the random forest, that the method that you want to use. So here, you import the random forest regressor package from the sklearn. Then now you initialize it. You can initialize or instantiate it, the same thing. So here you instantiate it or initialize it by calling it random forest. Then you give it n estimators is equals to 100, random state is equals to 42, and then the maximum depth is equals to 3. then you fit the model on the X trend and the Y trend, then this is what you get. Then you go ahead and predict the value. So it's like you are repeating the same thing. So you go ahead and predict. So you're predicting on the X test. Then you check the mean squared error. Is there a question? Yes, Ambale?
Yeah, hi guys. Sorry I came in a bit late and you had started.
Yeah, you were the one who was supposed to share your screen. Yes, yes.
Oh, sorry. I can even. No worry, I can share later on.
Okay.
My question would be the n_estimators. Are these like the number of models that we're trying to work with? That is the weak models. Is it? Are we?
No, the n estimators. Okay, the n estimators here is just okay. It's usually a default. Like it's a default choice. You can decide to give it anything, but it's just giving us like the goal of this is to give us a good balance between our model performance and our computational efficiency of our model. Yeah. So I don't know if you have understood it. So like when how can I explain it? Like to come here, like I mean something like if it can provide a good balance, that means that it helps us to reduce something, maybe things like overfitting, so that it can give us a more stable and robust prediction. Yeah. So it's not the what you've said.
Okay, thank you so much, Linda.
Yeah. Any other question? Okay, so I'll just go on. So from there also we check our MSC, like you're just repeating the same thing. But now this one is for the random forest regressor. So you can see our MSC here. Has it reduced or has it increased?
It has reduced.
So that means, what does that mean?
Model is performing much better.
When after ensembling, right?
Yes.
Yeah. So that means that after using the random forest, it has outperformed the previous that we used a single decision tree. Like it has outperformed it by performing better. And that means that at some point, maybe it reduced overfitting and it also reduced like the variance in the predictions. So that is how you say it like that. Actually, at any point, if you get any MSC, R squared, those things, you need to explain them. Yeah. So here I just gave some short notes. Maybe they'll help you when you get the notebook. Maybe I just wrote for model complexity, I wrote random forest is a simple learning method that constructs multiple decision trees and combines their predictions. Each decision tree in the random forest is trained on a bootstrap sample of the data and uses random subset of features at each split. But for a decision tree, it's just a single tree based on model that recursively partitions the feature space to make predictions. Then if we check out the variance, the bias variance trade-off, we can see that trees tend to have low variance, but tend to have low bias, but high variance, the decision trees. This means that they can capture complex relationship in the data, but are prone to overfitting, leading to high variance predictions. But if you look at random forest, they reduce the variance by averaging the predictions of multiple decision trees. So by combining the predictions of multiple trees trained on different subsets of the data, random forests tend to generalize better to unseen data, resulting to a lower variance and lower MSC, as you have seen. Then for ensemble learning, we say random forests leverage the principle of ensemble learning by aggregating the predictions of multiple weak learners. This ensemble approach often results in improved performance compared to a single decision tree, as it reduces the risk of overfitting and improves robustness. Then you can see to predict accuracy, I said, the lower MSC of the random forest model suggests that it provides more accurate predictions on average compared to decision tree model. The predictions made by the random forest model are closer to the actual target values, indicating better performance in capturing the underlying patterns and relationship in the data. Then the low MSC in the random forest is better at generalizing the unseen data, providing more accurate predictions with lower error. This improvement is attributed to its ensemble approach, which reduces overfitting and variance in prediction. So this one I was just giving some short notes just to showcase like how we've seen, like the first one, we've just built our model on a decision tree. Then here we came and used the random forest regression, which is an example of ensembling learning, just to showcase how it minimized the MSE, hence giving us a better performance model as compared to using a single decision tree. So therefore, we will go ahead and discuss the types of ensemble learning. Don't mind my spelling. With this, we will classify them to heterogeneous and homogeneous. So in ensemble learning, we have the homogeneous ensembles and you have the heterogeneous ensembles. So we'll start with the heterogeneous ensembles. So under heterogeneous ensembles, these ones consist of different types of models. So for example, Ambale can have decision tree, Mia can have a support vector regression, maybe Onesimus can have, let's say, a linear regression or something of the sort. So those are different types of models. So you can add them together and create now you can add them match in any regression that you want. So that is heterogeneous. That is what heterogeneous means. So the two types of heterogeneous include voting and stacking. Those are the two types of heterogeneous ensemble methods. Yeah. So I think I'll stop there just to check on you guys. And I hope I'm not going that very fast. Are you good? Okay, thank you. Thank you, guys. So from there, before I go on and discuss maybe voting and stacking, first of all, we have maybe to train our model on individual models, the way we did for the decision tree. So let's train it on a linear regression and see what it gives. Let's train it individually on a decision tree to see what it gives. Then let's train it individually on a support vector regression just to see what we get. So here, I just called the data frame another name. So the first one I'd call it data, but I just wanted to call it another name. So here I have the data set, then I read it, which is the same thing. Then I give the X and Y, which is the independent and dependent variable. Then now you have to scale it first. Then you normalize. Then now you test. So here you are initializing the scalars, which is the X scalar. Then it also scales the Y, which is the standard scalar. Then you normalize both on X and you normalize both on Y. So you fit this X scalar here, you fit it, and then you transform it to an array. Then the new axis, it's just like converting it now to a 2D array so that it doesn't give you an error. Then you normalize also on the Y, which is the Y scaled. You call this Y scalar that you've standardized here because you equated it to standard scalar. Then you fit it and transform it also on Y. Then you also reshape it so that it's okay. Then now you go ahead and now do the splitting, like the train test and the train test split, which is the same thing that you are doing. We are also using the 80-20% rule. The random state is 42. And now here what changes, now we are using the normalized X and Y. So here, where you are putting there up X, Y, here now you lose the one that has been normalized. And you remember we learned about scaling. Like normalizing, you want it to be in the range of 0 to 1. You are trying to minimize it. It was min max scalar, and sometimes you can use the standard scalar. So here you say X underscore scale, then Y underscore scale, then your test size, then the random state. Then after that, you instantiate your model, which is now the linear regression. You can call it any variable that you want. Then now you fit the model. So you're fitting it on the X train and the Y train. So after you fit it, you'll get something like this that show you that you fitted your model. Then you can go ahead now and here you predict. You're predicting on your X test, like the one that you're testing. So that linear regression is predicting on the X test. Then you can print your MSE, and the MSE is always the mean squared error of Y test and Y prediction. Then you can also print the RMSE, which is the square root of the MSE, the one that you've calculated above. Then from here, this one we explained it yesterday. You predict the line over the data. Then there you inverse and transform the domain. Then you go to a scale. Here you're just scaling. Then you transform it. Then now you plot now your scatter plot. So if you plot your scatter plot, you have the prediction line is here. Then you have now the blue lines are there, the actual values. Yes? Can I get an answer? Are they the actual values, the blue dots?
Yes.
Okay, thank you. So what can you say about this? what can we say about this scatter plot? Somebody kindly.
It follows a linear.
It's linear.
Yes, thank you. And also we can see that the actual values are not that far away from the predicted values, right?
Yes.
Yes, thank you. And what can we say about the MSE and the RMSE? Because you have an MSE of 0.068 and you have an RMC of 0.26. What can we conclude? So that is when we do when we fit the linear regression. What can we conclude? Can you say like is it performing better or is it performing worse? Like how can we conclude that? Now those are the things like we need now to understand, not just plotting and leaving the scatter plot like that. Yes, anybody? What can we say? Let me just do this so that you can see this one. This is the MSC 0.0685, then the RMSC 0.2618. So what can you say about that?
Can I chip on this?
Yes, kindly please.
So from the data we have normalized the data, and it is between the range of 0 and 1.
Exactly. Yeah.
And our MSC is 0.06.
Yes.
So even it is so much raw. I think it is rawer, which you may say that model is performing better.
Yes.
Yes, because having a minimum standard error of 0.06, it is good, and the root mean standard error of 0.26. It is assuming I may say that it is
26%. Yeah.
Yes, it is good.
Yeah, thank you. So we can say that if we look at our mean squared error and the root mean squared error, like they are very low, like they are not that big. So we can just assume, we can suggest that indeed our predictive model is performing relatively good while fitting with the regression, while fitted with the regression model. Yeah.
Yes, Linda,
Yes.
can we have John Warutere?
Oh, John, yes, because I can't see the screen. Thank you so much, Ibrahim, for that. Yes, John.
Oh, I had a question from yesterday. I was asking the MSE and RMSE, root squared mean error. What does it stand for? Because which one shows the model fit and which one shows the accuracy?
Does it show?
Because as I was going through the content, one is saying that one is showing the model fit, and the other one is showing accuracy of the model. So that's what I was trying to inquire.
Okay, nice. Anybody who can answer before I answer it? Where are my supporters?
The main difference between RSME and MSA is the measure, is the unit. That's the main difference. But the RMSE has the same unit as our data, but for the MSC are the squares of the target variable. So that's the main difference.
So I think to understand this, maybe I want somebody to tell me what is mean squared error. That's where we can start from.
Okay. Someone else or I can.
Yes, you can. Because that you can't. If John, do you know what is mean squared error?
The average square differences between the observed values versus the
variance.
The target values. Yeah, the variance.
So that means that So that means that doesn't give us an accuracy score, right?
So that MSE gives us the model fit, if it is fit.
The MSC.
Yes.
Mm-hmm.
So that's what I was asking. Is it the MSE that gives the model fit, or the RMSE? And then the other question is, which one shows the model accuracy?
I think the model accuracy you have to calculate it with there's a sky. Is it sky the package? Do you know the package that is called the accuracy score?
No.
I think
Not
we have
really.
done that.
Linda, in the content,
Yes.
they were saying that RMSE. I'm not sure, but
Okay,
they were saying that one is showing the model fitness, that it is fit for prediction, and the other one was showing the accuracy. So that's what I'm asking, because it is in the content, but I'm not sure. I did not understand exactly what they meant by that.
I don't think, on my side, I don't think MSC and RMSC directly measures accuracy of the model. Because they are only, I can refer them to metrics just used to evaluate the performance of the regression model. So what I know is, if you want to do an accuracy on something like a linear regression or something, you always do, maybe you can check at the precision, you can use something called recall. I know you've not learned about that. Somebody can go to check at the F1 score, or you can just calculate the accuracy score of the model. And what I know is that the mean squared error and the root mean squared error, they are both, like, they do the same thing, but at some point, MSC is always preferred over MSC. That's just, but let me see how but they both measure well the model is fitting, but I don't think they measure the accuracy. Yes, Lauren, kindly add your sentiments.
I think what I understood from the content was that MSC and RMSC actually do the same thing, which is they measure how accurate the model is. If it's low, it means that your model is accurate. But now the difference is what Onesimus has explained, that you would rather judge with RMSC because its units are the same as the original data.
Yeah, as the target. Actually, they are the same units as the target variable.
Yeah.
Yeah, that's right. So I wanted somebody to maybe explain to John, so that maybe he gets it better.
Okay, reader.
Yes.
The reason as to why many people stop at RMSE, because you have the test data, and you have the training data and the test data. So whenever you are creating an RMSE, you have the values that you want to predict. Then after the model predict the value, you compare the value you have with the result, because you have a Y test, you have X train and X test. Yeah. So you train your model using the train data and test using the test data. So
exactly.
You are trying to measure the LMSE measures the difference between the actual value you have value and the predicted value from the model.
Exactly.
So when there is a difference between, if you wanted to predict the number of years, let me say you have a data with years, you want to predict years, then the actual data you have, it predicts 2020. The actual data you have, it is 2020. The model gives you 2019. You have a difference of 1 year.
Yes.
That you can assume that is the LMSE. That's different. So whenever the difference of the actual value, the predicted value and the actual value is less, you always assume that a model is best because you're having a lesser error. Anytime until it gets to zero, you may not get LMSE of zero. You need one problem, you can't get that. But the target is always to get the LMSE of zero. Because if you get LMSE of zero, that means if you earn 2020, the model gave you 2020, gave you the value. Yes.
Yeah, that's true. And yeah, that's right. So just to answer what John said, I just want you to answer him. So which one between RMSE and MSE calculates the accuracy? That's I think, John, that was your question, right?
Yes.
Yeah, can somebody answer him after we've discussed all this? Because now we have a clear picture on what MSE and RMSE does. Come on, guys, don't let me down.
John,
Let's do this. Yes, Onesimus?
You use the LMSE to measure the accuracy because LMSE is the same unit with the data you are using.
Yeah.
You normally use the RMSE because it has the same unit as the data. But if you use the MSE, it is the squared unit. So they are not in the same unit as the data. So
yes. So the question is so the question that I want you to answer, John, is between MSE and RMSE, is there any of them that measures accuracy? Yes or no?
Yes, they both do that.
Yes. Okay. Good. Yes. Any other person? So you say yes. Okay. Yes. Any other person?
Repeat the question, Linda.
John was asking that we had calculated our MSE and RMSE, right? So he was asking that which one between the two measures the accuracy of this model that we are doing, like the model. So I wanted to know I wanted us to answer him. So okay, let me just pick RMSE alone. Does RMSE measure the model? Does it measure the accuracy of the model? That is what. Yes.
Yes,
it does. If you were to pick, I think RMSE is preferred because it is more accurate. Since RMSE, it's where we get the root mean squared of the whatever the values. Yes. So it means if there is any negatives, they are going to be removed. So it only uses positive values. Yeah, so it makes it more accurate from my understanding. I don't know if I'm correct.
Okay.
Okay, I have a question.
Yes. Let me see. There's somebody who was giving
I have a question.
Just ask.
Yeah, I saw Abdikadir's hand. Abdikadir will come later.
Okay.
Because if you check on MSC, that is the mean squared error. That means those errors are squared.
Yes.
So it's kind of double them. So they're like times 2. Then the root mean square, just the way like PG was saying, is now the square root. Now I'm finding the square root. If the error was maybe 3, then if you square that, I think that is 9, right? So finding the square root, we go back to 3 again. So that's why I think the root mean square is much more hard.
Go up and show me.
But in terms of maybe model accuracy, you also need to check on maybe the R squared also.
Okay. Thank you for that. I think, John, are you okay? No, Abdi. I think Abdi was to talk, and then we see how to do it. Yes, Abdi.
Yes, Linda. I think it was covered. I mean, we've spent a lot of time in discussing this. Yes, I'm not so sure about the accuracy, but I know that RMSE is the most preferred one to be used to check for the fitness of the model.
Exactly. Yeah.
About the accuracy, I think you have.
Me too. I don't think if our model is accurate or not. I think it just showcases how good it's performing or how good it's fitting, right? Yeah. So but I think
yeah. And then
also for the accuracy, there's no problem depending on how you are understanding it, because I think we are saying the same thing but different. I think we are understanding it differently, but we are on the same page. Yeah. Yes, that is it, Wairimu. But fit is all about yes. That is it. Okay, so for me, if somebody says accuracy, inanitupa nje kidogo. Yes, Carol.
I think, okay, I agree with everything, but I think the main distinction comes when we use MSC mostly to see, if you're trying to look at the difference between the outliers and the line of best fit. So that one gives you a better picture of like the fitness, but for the accuracy, I would still go for the RMSC.
Nice.
So I think they both literally just show the same thing. It's just that it just depends on what you're looking for, if you ask me.
Exactly. Thank you so much. Let me see the chat.
Yeah.
Ibrahim says the content is huge. Oh, yeah. Did I say something big, Ibrahim?
That was earlier on, don't worry.
Okay. Then Jabet says, just a minute. Then Jabet says they both measure how well your model is fitting the data, yes. PG says RMS is the same unit as the data, that is why it's preferred, yes. Then J Mungai gives us the basically RMS is the same unit as the model. It compares the model prediction on unseen data, X test with actual output Y test, yes. Then Ferris asks, how about R squared? Does it measure model fit? I think the R squared, most of the time it always represents the proportion of variance in the dependent variable that is predictable for the independent variable. And mostly it's usually between 0 to 1. 0 always indicates that maybe there's none of variability on the response variable. Then 1 indicates that the model explains a good variability. Yeah, I think that is what I know about that. Then J Mungai says RMSC gives us more explanation, assesses when you want to assess the model performance in terms of actual scale of the target variable. It provides more intuitive understanding of the average error in the units of target variable. RMSC is less sensitive to outliers. I think that is why it's picked, making it more robust metrics in data sets without outliers. Okay, thank you. Then Wairimu says, but fit is all about accuracy. Yeah, that's good. Thank you guys for those who are texting. Yes, Ibrahim, I think had something, then I go on very fast.
I think I've explained. Maybe I just wanted, like, you go up a bit and then we see the graph together with those values.
Here?
Yeah, together those values. I think if the predicted values are on that red line, and then the actual values are the blue ones, right? So for RMSE of 0.26 something, is like you are trying maybe to say that each value deviates or is far away from that line by the value of 0.261. That is like when you now standardize that, you say each and every value. But if you try to look at all those values, they're kind of like different values. And that I think that's what RMSC does, from my understanding.
Yeah, that makes even more better. Yeah, thank you guys. I think that was needed. So let's go. We are done with the. So we were going to fit like one model after the other. So we fitted our linear regression. We've seen how it's performing on our data, both training and how it has predicted it. Now we are going to the decision tree. I think these things you are now understanding them. I'll not be explaining the code so much unless there's somewhere you are seeing and you are not understanding what is happening. So the next thing we are instantiating our decision tree regressor with the maximum depth of is equals to 3, and then we are fitting it. Then also you calculate the MSC and RMSC. Then you do the same thing. Then you plot it. So for ours, let's just go with RMSC. Let me not talk about MSC. So for the linear regression model, we had 0.26. Then we are now coming for the decision tree. We have 0.40. So what can we conclude if we compare the linear and the decision tree? What can we say? Is the linear regression performing more than our decision tree regression?
Yes.
Yes, that's true. Then what about this? So that is about RMSC. So what about our how is it called, our function, like the predictor line, which is red? What is not happening? My laptop is hanging. Yeah. So what can you say about these guys? This, like the way it's moving like this way. What can you say about it? because you can't just draw it and then leave it like that. You don't do that. Yes, I'm waiting for your inputs there.
Linda.
Yes.
This graph gave me some headache because I don't know at those corners. I don't know that's where the node is where we now make the decision. Like I did not understand this line. Line.
Okay, the prediction now it has changed. It's just something like a step function. So you can see like the steps are moving. You see, so it seems like they are moving in something like discrete steps and like moving in a more smooth curve, right?
Yeah, in a more smooth curve. Oh.
Because you are seeing like it's, this thing is trying to make sure that maybe the values are like our model is predicting well. How am I saying it's performing well? I think something like that. That's why it's trying to create those corners. So you see that like these like those actual points are really, really moving close to it.
Yeah. Okay. So basically, if you look at linear regression, where we have
Let me just go up.
No. Just stay on that graph. Just stay on that graph. If you look on linear regression, we usually have like kind of straight line trying to
like this.
in between, like the baseline. So this is the same thing that this line is trying to do. Trying to those values.
Predictions.
Okay. Yeah. Thank you.
So what can you say from that? That's what I want now. Tuchangamke, let's cheer up.
I'm throwing the ball to Abdikadir. Abdikadir, we are together. Assalamu alaikum, alaikum salam. Just assist me.
You are just selected up. Can you tell us something?
Okay, let me have a look at that. Also, Anthony is raising his hand to join and provide an answer.
Okay.
Anthony, you may want to proceed here.
Okay, no problem. Yes, Anthony.
Okay, can you hear me?
Yes, we can.
Can you hear me?
Yes.
Okay, can we say that the decision tree graph is overfitting?
It's overfitting. Why?
Can we say that? I'm not sure.
Why?
Well, because of all this bending and bending, compared to the regression line, that's linear regression. It's that one is quite straight, but this one is doing too much just to ensure that it's closer to the.
Yes, but remember, yes, but remember, like the way you see the way it's making those corners. Can you hear me? The way it's making
yeah, we can hear you, Linda.
Yes, this is a decision tree. So like you see those transitions that are moving, like it's like it's representing the boundaries, like the decision boundaries that maybe the decision tree was doing, whereby the predictor variable is being partitioned maybe into subsets. So I think you can use that. Wait. I saw some hands. I saw Jabet. I saw Jabet, and I saw another person. Yes, Jabet.
Okay. We can't say it's overfitting because you see these are different algorithms. So for a linear regression, it is designed to plot a straight line.
Yes.
For a decision tree, it is designed to plot a line that looks like this. So whenever we have, like where we're having these bends, I'm thinking it's what Ambale was saying. Like that's where we are making the decision. Like that's where we are choosing.
Like the subsets, right?
Yeah, like now where the nodes are, our decision nodes are happening.
Yes.
Yeah, those are just different algorithms. For you to know if it's overfitting, you'll have to test the accuracy of the training data versus the testing data.
Yeah. I think Anthony, you are good. That's why I told you to reason the way I told you. And there's another person who addressed their hand before just gone. Are you okay?
It was me, but I also had the same argument as Anthony.
Okay.
I thought the model was trying to reduce the variance between the test and the variance between the actual and the test. So that was my idea. That's why the the lines are trying to reduce the space between the. You see, for the regression line in the linear, if you go up.
Let me just go up so that you see it. There.
Yes, you see. So my idea was it is trying to reduce this space between the line and the
predicted and the actual value, right?
Yes. So that I thought also of overfitting. It's trying to overfit the data.
Nice. This is becoming interesting. I like this. Yes, Abdikadir.
Yes. Actually, apart from the overfitting, is there anything else that tree is telling us? I mean, the step test. Because I can see, like, if we say these transitions represent the decision boundaries of the tree, and where actually the variables are partitioned into subsets. Apart from that explanation, is there anything else we can make up around this? Because yes, we have agreed, and it was clear in the Explore AI content that what decision tree does is actually overfit the model,
actually
in trying to actually reduce the MSE as much as get them. It's called they say normally to maximize the MSE when it's choosing the potential split points.
So what can we say? Any person who closes this chapter, Nemo, PG, Mildred, yes, Mildred?
I'm not closing, I'm just giving my opinion.
Okay, no problem.
The floor is still open.
Oh yeah, okay, no problem.
So now you see, when we were fitting the linear regression, let's go back to the linear regression.
Okay.
We said that the points are close to the red line, so that means it's doing a good job somehow. So I would like to say the same for the
decision tree,
because the blue lines are also close to the red lines.
Exactly.
So yeah.
Yeah, that makes sense. 100%. Actually, that's true. Even I've used the wrong word. That's true. We can see it like literally. But I think the only thing that is making I think the argument here is the reason why our predicted line is bended. It's because this is a decision tree and splits are happening. We have the data being divided into subsets. That's why it's showcasing the way it is. But for somebody, maybe we're saying maybe it's performing good and maybe it's overfitting. I think they are also giving a good argument on that, because now this is the point of this thing. Because I believe you can't have a scatter plot and you don't know what it's talking about. Like you don't have anything to say about it. I think all of you are correct. But I think the only thing we can just say, the reason why it has bended is because here we study. If it could be a linear regression, then it could be a straight line. There's a place where we are going to get something like a smooth curve actually, and you realize maybe we'll have used a different regression model. So I think from there we can be okay. If I close it at that, do I close it, or do I open more? Do I open more views? Yes. Let me see what Lorraine says. Lorraine says each step in the line represents a decision point where the data is divided based on a particular feature. Yes, Lorraine, and that's why it's making those curves like this way. Where am I? I'm on the screen like this. I think so.
So Linda,
oh yes, me.
So I want to ask a question. So you mean
who is talking? Yes, John. Then Ito.
So you mean every step, it's like when you are drawing that decision tree where it was greater than or equal to. So that and then you're separating, you move towards the side that is more convenient. So every step means it's a decision that is being taken.
No, I think the predictor variables are the ones that are partitioned into the subsets. So I don't know if those splits are the ones that are giving us those corners. I'm not sure about that.
Yes, I think what John is saying is correct. Yeah. Those steps are giving us is the way the algorithm works. Now, the algorithm is typically it's aiming to select the split points that maximizes the decrease in MSC in choosing each potential split point. And as a result of that, it's doing with years of experience, and that's why we're having. I think we should have maybe started with the decision tree so that we get clarity on that. And I think that's the reason why we're having this.
Yes. Yes, Ibrahim. Thank you so much, Abdi, for that.
Yeah. So my question is, on those steps is where the decision is being taken, is where the data is being split, right? So it's on those steps or on those corners.
I'm not sure. I'm not sure about that. 100%. I'm not sure about that. I can't lie. But I think Jay Mungai has given us something in the chat. He says that this is from Explore AI content. He says the abrupt transitions between steps indicate where the model changes its predictions based on the splitting criteria learned during training. These transitions represent the decision boundaries of the tree where the predictor variables are partitioned into subsets. So that's why maybe you have those transition of steps, those steps. So they're saying they indicate where the model changes its prediction based on the splitting criteria learned during training. Yeah. So I think there is something that that I've realized. Okay, but I'm not sure. I've just reasoned it right now. You remember, like for example, yesterday when I know this thing we are going to argue at the end of the lesson. We are going to argue, but I met with the Jebet and we came into a good conclusion with her today. But I think you see the way we were splitting that data. Let's say we are looking at the entire class and we want to see people who have age. Then they have given our ages. We are 38. And our ages, let's say, they range from 0 to 100. And maybe we want to give a threshold of less or equals to 30. So we went and made and asked if it's less or it branches. Then we check, is it less or equals to this? Is it less or equals to this? Then it branches. So you see, that is what was trained. We trained our decision tree. So I think that is what is happening here, because these now the steps are just giving the changes like in the prediction based on the splitting criteria that happened during the training. So that means there is a time it will go up, then it maintains again. Then I think it moves again, then it changes, because at the end of the day, the years of experience are increasing proportionally also with the salary. So I think that is something that I can add more, but I don't know if it has made any sense. Yeah. But it makes sense, I think. So yeah, thank you guys. Unless there is anyone being left, I don't like leaving anyone behind. Because if we discuss this, it sticks. And if it sticks, next time we just illustrate it very well. Yeah. So I think we are good there. And if somebody gets more insight about this, kindly just come to the chat or raise your hand and add something for us. So let's move on. So we are done with the decision tree. We've looked at the RMSE of the decision tree. We've gotten it 0.40. Indeed, it's performing well. We can say it's performing well, but not that well as compared to our regression, because our linear regression was performing at 0.26. So indeed, if we check on our data, we can see that our linear regression is performing well as compared to the decision tree. So our next one will be the support vector regression. And again, I won't explain because you are still doing the same thing. So you're instantiating the model, you are fitting the model, and again, you are doing the same thing. So this is becoming like a day-to-day practice now. So we are going, right now, we are getting the RMSE is 0.27. Can you see that? So we are getting 0.27. So for our linear regression, we had 0.26. Then we came to decision tree, we got 0.40. Then now we have come to a support vector regression, we've gotten 0.27. So what can we say about the RMSE of the support vector regression? Let's go, guys. Anybody? Those people who they never talk. I know you anyone, or I mentioned some names. Anyone, let's cheer up so that we can move. Anyone who can talk, just talk about the RMSE and say something small, then we go on. So that I don't just talk about everything. Yes, guys, let's do this. Okay, those people who have talked to them. Or I just go on. I think I can just go on if you don't want to talk. So I think yes, I can just go on because I can't talk alone actually. I just say it's okay. You can go and research later about it. Then you go ahead and now start building our heterogeneous ensemble methods. Yes, Ibrahim.
So sorry for that. I just wanted to tell you, just go on. But maybe just something that I can just say, like
I think I can just say I'll give you the notebook so you'll research, you'll compare them. Yeah.
Okay, no worries.
That's better. Then let's go on. Also, this one you can look at the way the curve is moving, and you can give out some insight on it. But this one I saw like it's something like just a smooth curve, and also you can see the actual values are also closer to the predicted values. Yeah. So I think we'll go on, and right now we are going to look at the heterogeneous models. And I've told you in heterogeneous models, we have the voting and you have the stacking. So I'll start with the voting. So when you talk about voting, you are combining individual model outputs through a kind of majority rule. So you are picking maybe, let's say, you are picking various models, but now while it's running, the output of the model will be done through something like a majority rule. We'll see that. So the process of prediction aggregation varies in the context of regression and classification tasks. So if you are doing a regression task, you'll take the average or weighted average of all predictions. And if you are doing a classification task, you lose the mode. The mode here means that the most frequently occurring prediction is the one that will be picked. Yeah. So I just gave out the steps, I think so. Was it the steps or I explained more about it? So voting is a popular technique used in ensemble learning where multiple models are combined to make predictions. Majority voting or maximum voting involves selecting the class label that receives the majority of votes from the individual models. So on the other hand, so that is the majority voting or maximum voting. Then on the other hand, the weighted voting. So if I talk about the majority voting or maximum voting, I'm talking about the mod. So you're selecting the class that receives the majority of the votes, like the mod. Then on the other hand, the weighted voting assigns different weights. So this is the one that you are doing now on regression task. Then majority voting, you're doing it on classification task. So if you're doing a classification task, you work with majority voting or maximum voting. This means that you have different models, multiple models. So you pick the one that has majority of votes, like the one that is frequently occurring. But if you come now to regression, you are picking the one that has an average or weighted average that maybe is the most. So that is why I'm saying, on the other hand, weighted voting assigns different weights to each model prediction and combines them, making a final decision. So both majority and weighted voting are methods of aggregating predictions from multiple models through voting mechanism and strongly influence the final decisions. Examples of algorithms that use voting in ensemble learning include random forests and gradient boosting, although it's an additive model weighted addition. Random forest uses decision tree models trained on different datasets. A majority vote determines the final forecast based on individual forecasts. Then I just gave here an example. So you have a dataset, then you have multiple models. So you have the linear regression model, you have the k nearest neighbor, you have support vector machine, you can have the decision tree, you can have logistic, it doesn't matter. Then now you do the voting. So if it's a classification if it's a classification task, you'll pick the one that is most occurring, the mod. That is where the decision will be made. But if you do now the other one that is average weighted, you now give weight of each of you give this one its weight to give this one weight to give this one weight. So it combines all of them, then it goes ahead and makes it makes now the final decision from those weights. Yeah. So I think, let me just go back here so that I see you guys. Are you good, guys?
Yes, we're good.
Okay. Thank you. Okay. So from there, we can illustrate this. So for the voting regressor, and again, you are just still doing the same thing. So you import the voting regressor from sklearn, the package. Then you define the models. So for example, the models that we ran earlier above, we had the linear regression model, we had the decision tree, and we had sorry guys, we had this one, the last one here, which is the support vector regression. So those were the models that we had. I don't know why my laptop is hanging. Just give me a minute. Yeah, it's now okay. So we had that. So you import it. Then now you come and pick the models that you are using. So these models are already in place because we had already instantiated them or initialized them above there. So we have the linear regression, we have the regression tree, we have the support vector regression. Then from there now you go ahead now and specify the weights of the averaging. So you can specify any weight of that model. So for example, the 0.1 is given to the linear regression, the 0.3 is given to the regression tree, and the 0.6 is given to the support vector regression. And now you call now the voting regressor, which is equals to voting regressor. It picks the estimators. The estimators are these models here above, and the weights are these ones here that you specified this one, where 0.1 is for linear regression, 0.3 is for the regression tree, and 0.6 is for the support vector regression. So you specify, you call it so that it specifies, so that it picks the estimators, which are the models. So it's picking those models, and also it's looking at the weights that you have assigned those models. So that is what you're doing. So after that, now you go ahead and fit it now. So you fit the model on the X train and the Y train. And for you, it is where X train, Y train, then this 0 that is here at the end, this one, the column command then 0, it's because you want it to select the first column of the target variable if it's multidimensional array. So that is why it's placed there. So
Linda,
what you get, yes.
Sorry, Linda, I just want to ask, what determines the weight? How do you calculate the weight that
you don't calculate the weight. You don't calculate.
Or how do you determine it?
You can assign it any weight that you want, depending on how you want your model to perform.
I thought the weight is dependent on, like, you are judging it that, okay, this one is more accurate than this one on this. So you are assigning weight for it to make the adjustments using that model.
Exactly.
Or you just, so how did it, is it after displaying maybe the linear regression, then displaying the decision tree? You can now say, okay, it fits more with this one, so I'll assign it a lower weight. It doesn't fit more with this one, so I'll assign it a higher weight. Is that the thought behind it?
I don't think so. But I think somebody can add on that, but I don't think so. Anyone who can add something on that, what Ray has asked?
Okay.
Yes.
So personally, I will be able to give the weight depending on the RMMC of those particular models. So if one model had a lower RMMC,
so which was linear regression, right?
I think it was SVR.
Linear regression and RMS, right?
Yeah, and SVR, give them a higher weightage compared to the decision tree.
Nice. Any other person? Guys, please talk so that I don't feel I'm alone.
No, you're not alone. You're not alone, Linda.
Yeah, we laugh at you.
You're not alone. Sometimes we
you just listening. Okay, I get it.
Yeah, you're not alone. Maybe basically what I can say, I did not hear what Kito said.
What Kito said?
Yeah, I did not hear that.
Okay, Kito said. Okay.
Yeah, but I heard what Ray said, and I was of the same opinion that maybe if I'm giving the weights to these different models, then I will consider which one that I think performs better than the other one. So I don't know if that is the criteria or the procedure.
I think so.
Weights. Because from the three models, linear model, the one that you have now, linear models were the linear model was 0.26, then followed by the SVR model at 0.27, and then the regression was the last one at 0.4. But if you try to look at the weights that we have given these models, then you have done the vice versa from what you're trying to deliberate on.
So I should interchange.
Yep. Maybe you can have Ferries, Namax.
Yes, Ferries.
Hello, I think you can hear me.
Yes.
I think the model weightings, I think the weights are assigned based on the performance of the individual model. I think I think this is also based on intuition, because from the previous individual performances of the models, as we have seen, we've sourced that linear regression, linear model performed better than the decision tree, right?
Yes.
And also the SVM also did better than the decision tree.
Yes.
Yes. So that means that even these weightings, you can also just vary the ratios and see the output. Yeah. So this is also what I also did. I also ran this, and then I realized that when I changed the weights I increased the weight for the linear model and also reduced that for the decision tree because it didn't give a good RMSE. I realized that the RMSE also become it also changed. I think it also got to be
smaller.
I got a lower value, exactly.
Like a better value.
Yes.
Nice.
You can vary the model weightings and also check the output and see which one will be a better result.
Okay, thank you for that.
Yes.
Thank you guys so much. Any other person? But I think now that's clear. And thank you so much, Ray, for bringing up that. Was much needed. Thank you so much. So I think we are good. PG says the models are weighted. Yes. I think we should now agree on that. I think now make sure that you check on how they are performing and give the weights according to their accuracy, like the way the models are. The models were predicting, like the way they were performing, like their contribution on the prediction. Yeah. Yes, Ambale?
Yeah, and that's just to add something, maybe a follow-up question on what Ray raised earlier on, is that the weights, are they supposed to be like in floats, the decimals ones, or they can be like a whole numbers, integers?
I'm not sure.
They are in percentages, so they have to add up to like 1, between 0 and 1.
Okay, thank you, Jabet. 1, baby.
Jabet.
Yeah, they should add up to 1. I hope you guys are keeping that into, like, it's sticking in your minds, because if it sticks, you'll never have that problem again. So we are good. So I don't want to run this notebook again. So I don't want to, because that means I'll have to go back to I'll have to run the entire cells. So that's
No. Let us just stick. Don't run it. Let us, as long as we've understood, let's just go.
Yes. Okay. Thank you. So after that, I said now we'll go ahead and fit your model. Let's explain to you what this does. So it'll get you fitted. Now we have 3 models. Under voting regression, we have the linear regression, we have the decision tree regressor, and we have the support vector regression. So after that, now we go and check the performance and voting ensemble. So after checking, so this is like you are repeating the same thing. Actually, the more you repeat doing this, the more now you understand what is happening. So from there, now we came and our RMS is now 0.3. But I think I have now 0.3 because of how I chose the weights. So don't mind that. So we are coming and now we are getting 0.3. So what can we say? Because I believed it should have performed better. Let me just go back so that you can see it. Yes, guys, let's contribute now. What can we say? Yes, Jabet?
So do I answer based on the 0.3 comparing to the others?
Yes, you can answer based on that, but you can try and say if you got a smaller value. Yeah.
Okay, so if we got a smaller value, we will say that the Ensemble model is performing better. But if this was the value, the best value that we got, then we could just go and pick one of the other model that performs best,
which is linear regression, right?
Which is linear regression.
Exactly.
And use it instead.
Thank you so much.
I think also, but I'm not sure, we could also remove the least performing model and redo the voting process again. So we can remove the regression tree and then redo
the linear regression.
The voting process.
Yes. That's true. Yes. That's true. Thank you so much. Yes, Anthony? Yes. Anthony? Or you did a mistake. It's okay, but it's better like making a mistake on raising a hand or giving a thumbs up, but not a down.
Can you hear me, please?
Yes.
Okay. Sorry about that. I think my earpiece was malfunctioning.
Okay.
I was going to say that based on the questions earlier asked by Ray and somebody that contributed, that I was saying that you can fine tune it by reducing or tweaking the each weights. When I went to check on the ChatGPT, how is there any way to automatically determine the best way to ascribe to each of these models during the assembling method? So it says that there are some models that we can use to calculate this automatically, so that it helps us in fine tuning it. So it mentions some models like breed search, random search, optimization algorithms, meta learning approaches, assembly learning frameworks, that is a voting classifier. He said these methods allow for automated determination of the best weights to give each model in the ensemble, saving time and effort compared to manual tuning. So maybe later on, if someone has done the adjustment and see, we can also have a further tutorial on how to apply that in getting the best weights to ascribe to each of the. So we need to now be using manual method, and we don't need to now remove any model. The thing will just by itself adjust the weights based on the performance of each of the models. Thank you.
Okay, nice. And that's what Jebet has just described in the chat. That is hyperparameter tuning. Yeah. So we are good, guys, right? I hope these things are sticking, so that when you are building your models, you play around with those weights and make sure that your model is performing well. So, and also there's something that I read online about voting, and I think you can go more and search about it. There's voting. There is always voting. Like there are two methods of performing voting. There's a hard voting, and there's always a soft voting. So for hard voting is equivalent to majority vote that I've just described. Then for the soft voting is essentially averaging out the output. So the same way, like you're saying, averaging the weights, the same. You can tell somebody that is hard voting, and for soft voting, you can tell them that is when you pick the majority of the vote from the models from the regression models that you've been trying to check which one is that we've been trying to pass through and fitting it to the model. Yeah. So you can also use those terms. So if you hear somebody saying soft voting, hard voting, yeah. So you can. It's still the same thing. Yeah. Then I think so. That is the first method of ensembling, which is under heterogeneous. Then you also have stacking. So under stacking, they're saying stacking is a strong ensemble learning strategy in machine learning that combines the predictions of the numerous base models to get a final predictions with better performance. So this is combining the prediction of numerous base models. Then it gives the final prediction with the better performance. So stacking is also known as it's also known as stacked ensembles or stacked generalization. This I got from I copied this from my Medium post, sorry. So the primary idea of stacking is to feed the predictions of numeric-based models into a high-level model known as a meta model or blender, which then combine them to get the final forecast. So this is an illustration. I think this one I got from, where did I get from? Was it from Explore AI? So you have the input data and then you have the base. We have base learner 1, base learner 2, base learner 3, base learner 4. And now you're getting you are combining the predictions of those base learners. So we have a prediction 1 from base learner 1, you have prediction 2 from this one up to prediction n. So you're combining it now to a meta learner. There's a meta learner now after you've moved from the base learners a prediction. So it goes to the meta learner, and then from that meta learner is now when it makes the final prediction. Yeah. So I think there it's well explained, or if somebody wants to add something before I move on. Are we good, guys? Or is it confusing? Are you good with stacked ensemble? Nice. So I just gave out the steps, maybe the detailed description of how it works. So preparing the data, the first step is to prepare the data for modeling. This entails identifying the relevant features. You clean the data, you divide it into training and validation test sets. That's what you know. So model selection, after you've prepared the data, now you choose the best models that will be used for stacking ensemble. A broad selection of model is simply chosen to guarantee that they produce different types of errors and complement one another. So maybe you can now choose the different types of models that you want to use as your best models. Maybe one can pick regression, another one decision tree, another one stacked, another one logistic, whichever, random forest, whichever method. Then now training the best models. After selecting the best models, they are trained on the training set. To ensure diversity, each model is trained using a different algorithm or set of hyperparameters. Because now you are coming here, you are training this model, you are training this model, you are training this one, and you are training this model. Then from there, now you come and predict on the validation. So when the best models have been trained, they are used to make predictions on the validation set. So here now, after you've trained them, now you make the predictions. And I think you people know what the validation set is. So you make the predictions on the validation, you make the predictions, it makes predictions. Then after it makes predictions, you develop a meta model. The next stage is to develop a meta model, also known as a meta learner, which will take the predictions of the underlying models as an input to make the final prediction. So this meta learner will take the prediction from the first base learner, it will take the prediction from the second base learner, it will take the prediction from until it finishes all the base learners that you've given it. Then now it takes those predictions and it will use those predictions from the best learners to give us the final prediction, which is now our output. So that is what it does. So any algorithm such as a linear regression, logistic, or even a neural network can be used to create this model. So here on the meta learner here, you can use any regression model. So you can decide to use linear, you can decide to use random forest, you can decide to use logistic to make now the predictions that are coming from your best models that you had initialized earlier, that had been trained with the data set. Then now you train the meta model. The meta model is then trained using the predictions given by the best models on the validation set. The best models predictions serve as features for the meta model. Then now making test set prediction. Finally, the meta model is used to produce the test set predictions. The basic model's predictions on the test set are fed into the meta model, which then makes the final prediction. The final stage is to assess the stacking ensemble performance. This is accomplished by comparing the stacking ensemble predictions to the actual value of the test using evaluation model. So these accuracies, I think we'll learn them at we always have things like F1 score, recall, precision to check how your model is accurate. But I think now for us, we'll just test using the RMSE. So I again give you another model here just to show you what is happening. You have your data is trained. Then it goes to the best learners use that trained data. Then it gives now the prediction. The predictions are used by the meta learner. Then the meta learner now they give the final prediction. So in the end, the goal of stacking is to combine the strength of various base models by feeding them into meta model, which learns how to weigh and combine their forecast to generate the final prediction. This can frequently result in higher performance than utilizing a single model alone. Yeah, so that's all about stacking. I don't know if I was fast, but I've tried to explain it better. Have you guys understood, or should I repeat? Was it
Can you repeat a bit?
Was it yes?
Can you repeat once more kindly?
Okay, thank you. I'll just go in one more time. So this is the diagram of like just showcasing what is happening. So before you start building a model or doing something, or before modeling, you always prepare your data. Maybe you identify the relevant features. The features are always maybe the X variables to identify your target variable. You clean your data. You make sure you have the training and the validation sets of your data. The validation sets actually is the test set, if I'm not wrong. So then you come and select the model. So by selecting the model, when it comes to stacking, you pick the models that you want to use. You can pick as many as you want. So you can decide to pick the model which will be the first one, and you can call them as base learners. So that's where they come in. So the first model here is the base learner 1, the base learner 2, the base learner 3, and the base learner 4. I think up to there you are good now. Are you good, Ambala? I'm going with you now.
Yeah, I'm good.
Okay. So from there now, you come now to train those best models that you've chosen. So after you've selected the best models, now you train them using the training set that came from here. Do you get it? So after they are trained, and each of the model is trained using a different algorithm, because all of them have different algorithms. They are not the same. So maybe the first one is linear regression, will be trained differently. The decision tree will be trained differently. If you had picked a support vector regression, it will be trained differently. Then after that, now you use those base models to make now prediction on the validation set of your data. And I think the validation set is the test set. So after you've trained those models that you picked to be your best learners, you use them to make predictions on the validation sets. So those predictions are the one you are seeing here: prediction 1, prediction 2, prediction 3, all the way to prediction N, the one that you've been chosen. So those predictions are the one that will go into your meta learner. So the next step. So the next step is you choose a meta learner, and a meta learner is just like a meta model. You can choose any type of model that you want to use. You can choose to use a linear regression, a random forest, like a decision tree or something to be your meta learner. So that meta learner, it takes now the predictions that were gotten from your base models, right? So that it can give us the final prediction. You see? So the meta model is trained using those predictions that were gotten from the base models. Then after that, now it produces the tested predictions now for our model. Have you understood that?
Perfect.
Okay, thank you. Let me see. Yes, Ferris? Just go ahead. Just
a question.
Yes.
Those predictions that you've now fit into the meta learner.
Yes.
Are they averaged predictions, or they're weighted averages of those predictions from each of the individual models?
Each of the individual model. Because each of the individual model performs differently, and it will give a different prediction after working on the training set. So after Tuseme, you had logistic regression, me, I had linear regression. So me, I'll give my prediction from the training set, because I have a different algorithm. Because you are using logistic, you'll give a different prediction because you're using a different training set. You are using a different algorithm, but on the same training set. Then now those predictions, mine will be prediction 1, yours will be prediction 2. So it goes into the base model that you've chosen. Let's say maybe it's a random forest. So that random forest picks all those predictions, then now bases on them to make the final output. Yeah.
All right.
Okay. Any other person? If you are good, just give me a thumbs up, and then we go on and see what is happening.
I have not understood what
Yes,
you've
PG?
explained
Yes,
to
PG?
the person. I'm saying,
yes,
I actually have not understood what you've explained to that person when you said whether we are doing because you see, we've trained several models, and then we are doing a meta model. So you're saying the meta model is using all the predictions.
Yes.
So
yes.
How exactly does it use all those predictions? Does it then repeat the whole process, or what becomes the test set? What becomes the training set? Imagine now we have this meta model, and maybe the meta model is just using maybe even let's say even just linear regression, and then it's taken all these predictions. So does it do training test for each set of predictions, or what does it do? Does it average, or what does it take the best?
Actually, what does it do? So you see those predictions, you see the way these predictions are entering the meta model. So this meta learner is treating this prediction as features. You see, like those predictions are serving as features for this meta learner. So it picks those predictions from both of your best learners, then it works maybe underground, like itself, now to make the best prediction out of them, like to give us now our final prediction that it believes is the best.
So it's using from my two best learners, not all of them.
Using
what did you say?
I don't think it's picking the best. It picks all of them because it's stacking.
So the other question would be, when the data is going now to this multiple models here, base learner 1, base learner 2,
this one, yes.
Is it split or is it the whole set of data that
this one is now when it's going out, it's going out because it has been nearly on the, is it the validation set?
No, because I'm asking when it came in, when it's coming to the base learners from
when it's coming in, it's coming as a training data.
So I'm asking, is it the same data or is that data split into several?
You see, the first thing that you have data, you always have the training data and the test data, right? So
yes.
The training data is the one coming in. Then it's coming into those base models that you've assembled, right? Then when it comes in, they are trained, like the base models are trained on now your training set. Then
Linda.
Yes?
Linda,
I'm not sure you understand.
PG, I think I can answer you.
Yes, please.
Okay.
So when we are using that train set, see, we've already split train and test.
Yeah.
Yes.
So now that train set is used, the whole of it is used for each of those models. So it's the same train set that is used on linear, the same train set is used for the other models, and then now it
like
makes
for all the base learners.
Yes, but of the same train set is used for the different models.
Yes.
So linear regression gives a different prediction based on its strength. The other model gives a prediction based on its strength, and then now the meta learner tries to combine all those, and then it gives the final prediction.
Okay. I think I get what you mean, because it was a bit confusing when they were coming in. So that all the train and test sets for all the learners are the same, and then it uses now those predictions to build up on that and create the best, like the outcome from the meta learner. Okay, thank you.
Okay, good job, Lauren. Any other person? I think we are good. I really want to finish all these things today. So from there, you come and do the same thing. So you are doing stacking. So you import the stacking regressor. Then you pick the models that you used as base models. So for here, it's linear regression, the regression tree, which is the decision tree, sorry. Then you have the support vector regression. And then for stacking, instead of now picking the weighting as the way we have been doing voting, you now pick a meta learner model. You see? So you come and pick any meta learner. So for here, we picked the linear regression. Then after that, now you come and call it so that you indicate your estimators, which are these models, and your final estimator, which is the linear regression here, because this is the last meta. That was the last meta learner. Then from there you come and fit it. You can see like the first base learners were linear regression, decision regression, and SVR. Then the final estimator, which is the meta learner, is the linear regression. Then you come and do the same thing. So this is just like you are repeating yourself, because you just want to see how are they performing with this. How is it performing on this? You see? So we come and get this. So this is how it's performing on when you do stacking. So we can see as compared to, was it voting? We can see our RMSE now has reduced a little bit, but still it's not performing well as the way we used the individual linear regression. Yeah. So this is how it looks like. So anyone who can add something or who has not understood, so that you can move on. Yes, guys. Are you people good? Like, are you contented? Yes.
Yeah, personally, from my side, I'm
good.
far with you.
Mildred is good. Kito is good. Where are the rest of you? Lauren is good. Ibrahim is good. Ingrid also says good. Yes. Fairies. Thank you guys. Thank you guys so much. So I think we can move on. I was writing some small notes for you there, so I think maybe you can see it. So we have done with the heterogeneous. So heterogeneous, I think you've understood it. So we are coming to homogeneous ensemble. So when you come to homogeneous ensemble, a commonly used example of an ensemble model is the random forest. Random forests combine multiple homogeneous models, i.e. decision trees, to make predictions. In homogeneous ensemble methods, diversity in model performance is promoted by the ability to control the number of predictors or portion of data supplied to each model in the ensemble. Some of the most common methods for combining homogeneous models is the bagging and the boosting. So these are the two. So for heterogeneous, you have stacking and voting. Then for homogeneous, you have the bagging and boosting. So I think let me just add something here before we go on. So I think I needed to say homogeneous. Just a minute, so that homogeneous. I'm always bad at typing. Ensemble, because I don't know how to type with the two hands. Imagine combines.
You and Nehemiah same WhatsApp.
Yeah, I don't know how to combine to type with the two hands. I usually use even half one finger. I usually find it very hard. Of the same type of model. I think this one looks good now. Let me just try it. Yeah, that looks good now. So that we have the definition of homogeneous ensemble learning. So the other one combines different versions. This one combines multiple versions of the same type of model. The other one combines multiple versions of different type of models. So let's look at bagging, or aka bootstrap aggregating. So they say bootstrap aggregation or bagging is a technique that improves prediction accuracy of combining predictions for multiple models. It involves creating random subsets of data, training individual models on each subset, and combining their predictions. However, this only happens in regression tasks. For classification tasks, the majority vote is typically used. Bagging applies bootstrap sampling to obtain the data subsets for training the best learners. As such, the resulting bag of models are together more stable due to decreased variance error. The predictions are made by aggregating the predictions of all models in that bag, like the bagging. So in short, bagging is a technique in which numerous instances of same base models are trained on distinct portions of the training data. I don't know if you're getting that. It's saying bagging is a technique in which numerous instances of the same base model is trained on distinct portions of the training data. The subsets are generated via bootstrapping, which involves randomly selecting the training data with replacement. Actually, that is a very important point. Each base model is trained on its own bootstrapped subset of data. Then the learning model then forecasts at the integrated using voting or averaging procedure to the final prediction. So this is how it looks like. So you have subset 1, subset 2. Then you train into a learner. Then the prediction. Then those predictions now are picked as now they are picked as an aggregator or using volume and using voting. At the end. So I think I've explained here better. So I'll read as we go back to check what is happening. So they say select a base model. So select a base model that is known to perform well on.
Before you go, Linda, please.
Yes.
Linda.
Yes, I'm hearing
you. For interrupting.
No
I'm
problem.
asking, what does replacement mean, or we learn as we go down there?
No problem. We will learn, but we can also talk about it before we go.
Okay.
No problem. I think with the replacement is the way you have a bottle, then it has balls inside it. You see? So I tell you, PG, pick one ball from this bottle. Then you pick that ball. Then I ask you, what color is it? You say red. Then I tell you to return it. So with the replacement, you return it, and then the next person, let's say like Lorraine, picks another one. So you are picking with the replacement, not with the. If you pick without replacement, that means you are picking, then you leave it at outside. You don't go ahead and pick it. But with replacement, you are picking it, you are looking at it again, you are returning. Then the next person, which is Lorraine, picks another one, again returns, and maybe let's Ferris also goes and picks and also return it. Yeah. So that's what it means.
Thank you.
Good? You are welcome. So let's move on. Thank you so much for that. So where am I? I'm opening the wrong notebook. Yeah, I'm here. I think so. I think even I can just go. Even this one is good, but you can. I've just given you a small screenshot, but I think we can just do that. So you select a base model. Actually, this one you must be very keen because it's usually confusing. Like it inaweza kutupa nje. It can throw you outside the box if you are not keen. So you select a base model. Select a base model that is known to perform well on a particular task. The base model should have a high variance, which indicates that it overfits the data. Then after that, you do now bootstrap sampling. So using random sampling with replacement, create numerous subsets of the training data. So you can see that now the bootstrap samples are here. So you have subset 1, you have subset 2, then you have subset. Like you are splitting now, you are bootstrapping into samples with replacement. That's what they're saying. So use random sampling with replacement, create numerous subsets of the training data. So this training data that is entering. Then Ensemble decide the number of base model is equal to the number of subsets performed. Each subset should be the same size as the original training data, and each data point should have an equal chance of inclusion in each subset. This is known as bootstrap sampling, and it aids in creation of variety among base models. I think I'll stop there first because I want us to understand that concept of bootstrapping before we go on. I just want us to get until here where we have reached, because this one is not that easy to understand easily, like very fast. That's what I mean. So I think that is where we have reached. Is anybody facing any confusion so that we can help?
Yes.
PG faces confusion.
There's something that you've read that you've said. Each subset should be the same size as the original training data. How then is that a subset? In this, just you can go back to what you were reading.
Yeah.
There's a place you said each subset should be the same size as the original training data, and each data point should have an equal chance of inclusion in each subset. How is a subset, if it's the same size, then that is essentially the same as the training data?
Because you are picking and replacing actually. You have a training, you have a training data. Okay, if I don't explain it well, I think somebody can explain it better. You have a training, our training, actually, let me just move here above. I think I've understood it. This is your training set. So this is why we are bootstrapping like we are doing the bootstrapping sampling. So this training set, you see the first subset will pick. Then again, you will replace that data to go back to the training set. Then now this one will go and pick it again. I don't know if you're getting it. So you'll realize that every subset will have the same size as the training set. Like we'll have used the same size of that training set. I don't know if you are getting it. Or anybody can explain better if for PG, please. Yes, Ferris.
I think the reason why we are sampling with replacement is so as to maintain the size of the data set, yeah? So that the training set is the same as the bootstrap set. Yes.
Yes, exactly. PG, are you still lost?
Let me be a devil's advocate and ask a question.
Yes. Okay, just a minute. Who is talking, Jebet?
Yeah, I want to ask a question.
Yes.
As a devil's advocate. So now if we are replacing it, like we are picking with replacement and we want it to be the same size, so that means all the data set will be the same.
That is the goal.
No, like it will be the exact same thing. Like I'll be training on the exact same data.
But that is the same. You should train, and that is the goal. You should train on the same exact. Every subset should train on the.
So that means I won't have any difference. Like there won't be any difference.
Can I talk?
Because then why are we doing subsets? Then
Yes, I think it's becoming interesting. Yes,
okay, Can I talk? Okay. First of all, can we agree, Linda, that we are training these subsets on the same model? If it's linear regression, it's linear regression. If it's a decision tree, it's
so I think that one. I think somebody that should learn that is Jebet and PG. So I think
okay, Jebet and PG. Can we agree on that?
I don't have a problem. Okay, personally, if that's okay.
Okay, can we agree that we are having different subsets, training them on the same data? Are we together up to there? Yeah. So what we do is this one. We have 100 data sets, like all the data sets that they are 100. So we want to select 80% of them for training, 20% for testing. So this 80%, after we have picked our 80% the first time, then we see which numbers are these. Then we set them like we set them aside. Then we also kind of like return all those numbers again into our training pot. Then we also pick again the 80%. I believe without using that random underscore state, there will be different numbers.
Now let me
pick like the same thing. Because here I believe the subsets need to be the same size but different. Because if the same thing, then you're doing zero.
So how will they be different if they're exactly the same size and we are picking the exact same data every other time?
Okay, like for example, we are having 5 numbers, right?
Yeah.
Then you want to pick 4 numbers.
Mm-hmm.
So after picking our 4 numbers, maybe we pick 1, 2, 3, and 5. We write aside 1, 2, 3. 1, 2, 3, and 5. We write it's like we write aside 1, 2, 3, and 5. Then we return all the numbers again into that basket again, and then we pick again. And this time we pick 1, 2, 4, 5. We write those numbers aside. Then we return them again. Then we pick, and this time we're picking 3, 4, 5, and 1. We something like that. Hope you understand. So that these subsets, they're like different subsets, but of the same size.
So in according to what I've gotten from you, it's actually like it's not 5, it's 4. Like it's the subset of the 5. Like it's not going to be the whole 5. It has to be like 4.
Yeah, like that. 4
exactly. That's what I'm understanding.
That's what you mean. That's okay.
Yeah. Like
I feel like that statement is a bit confusing when you say it should be the same size as the original training set. Because like you say, when Linda, you had said you pick a ball, it's red, then that is the first subset. Or you could have picked 2 balls. One is purple, one is red. That is the first subset. Then you return those 2 again. And then now when you're coming to pick subset 2, you might end up picking the red one and another green one. But they are all the same size, but not equal to the original training set.
Exactly.
But then if they were equal, we are just doing the same thing.
It's the same size. It's not equal. I think I can, let me just use another example.
Okay.
So let's say,
maybe that statement is where the issue is.
Yes. Let's say
statement.
Yes.
Linda.
Okay, yeah.
Linda, can I also, I'm now understanding PG.
Yes.
So when you are now drawing our training test, are we our training subsets, right?
Mm-hmm.
Are we drawing our training subsets from the training dataset or the original dataset?
The training.
Yeah, Kito has answered that, the training. Let me give you an example. Okay, I have me, let me use PG and Jebet because they're the ones who have a small like glitch. So like PG is here, Linda is here, Jebet is here. So me, I'm subset 1, Jebet is subset 2, and PG is subset 3. Then you have the training. We have the training. The training set. So we are saying each subset has the same size as. Was it the original? Just a minute. Let me just check so that I cross check well. Just a minute.
And just as you check, a question has come up into my mind. The three of you, when we combine the three of you, are you now the training set, the three of you?
Okay, there's something that I've understood. I think the size should be the same as the original data set, not the training. Exactly.
Yes.
Because from the original data set.
Confusing. That's why PG and Jebet are confusing. Actually, I've seen why they are confusing. So the size of it should be the same as the original. But now the subsets, the subsets now are the how can I bring this? But I think if I use an example, it will be good. I picked PG, me, and Jebet, and let's say me, I'm subset 1, PG subset 2, and Jebet is subset 3. So me being subset 1, I should have the same size as the original data set. PG should have the same size as the original data set. Jebet should have the same size as the original sets. So let's say, for example, our original data set had 1,000 data points. That means each subset will also have their 1,000 data points. So this means that each subset has a chance of being included, and that's why we have with replacement. So no matter how many data points can be included multiple times, while others cannot be included, the goal is that the subset should be the same size as the original data set. So I think that is where we were confusing, because even it's written here. It creates numerous subsets of training data. So those subsets are the ones that now have the training data in it, but they should be the same size as the original data set.
Yeah. Okay, Linda.
Yes.
You're getting me more confused when you say about they should be the same size as the original data set. Does it mean that now we don't have a training test?
You have it.
Okay.
You have it.
Because you are kind of like, I'm being confused.
The subsets are the ones that have the training data.
Yeah. And you're telling us that those subsets...
They should be the same size as the original data set. And the original data set is always...
I think that doesn't make sense. Because now if the original data is 1,000, and then now we split it into train and test, and then now the test is what we are creating the
test will validate with, it's the one that will be used to validate, right?
The training set
is the one going to is the one that is being used by them.
Yes.
Subsets.
So if we have 1,000, then we divide 80-20. So 80 will be 800. Right? Then from those 800, we are taking those subsets, right? And then what you're saying is that these subsets should be the same as 1,000.
Okay, so the goal here is that even if you are not, okay, your training data will now become, okay, I think I can give another person to talk because
Linda, can I try to explain?
No, let another person talk.
Linda. Guys, hold on. Linda, can I talk?
Yes, kindly go.
Can I talk?
Yes, go ahead. And then after Anthony, I think Abdi had raised his hand. We hear from Abdi. Then let's see if people will still be confused.
Okay, guys. We already know that to train a machine learning, we have to split the data into tests and train. So it makes no sense that your subsets will not be looking at your test data points. So what Lila is saying here, before that question came in to confuse us or confuse us, is that each of these subsets should have equal chance of picking from the original training data set, not the old data set. It's from the training data set that each subset will show, and each subset should be of the same size as every one of them. So a subset should have 10. Another subset should have also 10 samples. So one subset should not have more sample than the other. And if the original data has 100 population, so and I have split it into training and testing. Let's say 80-20. Out of that 80 of which constitutes the training, and you have 10 points, 10 subsets. Each subset should have let's say 8. And when one picks its own subset, it should replace what has picked, so that the next person that will pick has equal chance of picking any of the 80. So that each picking, the subset is not the data point is not being reduced. It's being replaced at each picking. So the main statement there is saying each subset should be the same size as the original training data. Forget that statement. What is important that we understand that when the subset is speaking from the old training data set, having splitted it into 2 parts. So when you are now, when I pick picking, you pick with replacement, and your each subset should be of equal size as the next subset, and they should be of equal. They should be from the same training data. I hope that helps. Thanks.
Just a minute. What is the size? What is the size of data? What do we mean by size of a data? Yeah, that's where I think that's where I can start from. What is the size of a data frame? How do you get a size of a data frame? Yes, I want to hear from you guys. What is the size of a data frame? Yes, I'm waiting. Yes, what is the size? Because what is the size of a data? What is the size? How do you get a size of your data frame? You have your data, you've read your data frame, you've looked at your info, you've looked at, how do you get the size of your data frame?
The number of rows.
And the shape, actually, right? Then what is confusing you guys?
I think people are not understanding that when you say that the subset of the data should be it should be the same as the original data, like the number of rows, and they're thinking like you've already chosen for training, so how will they be the same? But me, I've understood, because from probability, when you do that in terms of probability, it makes sense when you're saying that the size of, if you had 6 balls and you picked one and you return, you'll still have 6 balls. That is what I think is confusing.
That means it's the number of rows, right?
Yes, the number of rows.
Yeah, that's the point actually.
Yeah. How are they random though? The question is, how are they random? Because that means we are still using the same.
They are random, because if you have 6 balls, PG, and then you pick one, you pick to say 6 colored balls, you pick one, and then you return it. Somebody else, you want to tell me the next person who will come to pick will pick the exact same ball that you had picked?
Nemo, I think what I'm asking is, if you're picking one, then is the subset 1 or is the subset 6?
No, I'm talking of let us assume the subset. Let us assume the file, it is one subset. When you pick one and then you return, somebody else comes and picks the same subset. He will not pick the same thing as you picked.
I think Nemo, you're not getting what I'm asking.
Nemo, let me ask.
The training data is a bag of balls. Then you say I pick one, and is that one ball the subset, or what is it in this context?
Is part of the subset. See, subset is part of the data. Ama?
Yeah, Nemo. Nemo.
No, it's okay.
Nemo. Hello, Nemo.
Yes.
Yeah, I think that one is the subset. And what PG is trying to ask What is it? For me, I think it's the subset. And then we now return it again with it, when we are now talking about replacement. There's an equal chance for somebody else to pick the same thing with replacement. So it does not mean that when you return it, that someone else will pick a different thing. No, they can pick a different thing, but there's an equal chance to pick the same thing or anything else if you replace it. I see so many hands. Can I allow them in?
Wait a minute. I really like this. Jabet, then Anthony, then I think I saw somebody like John. I think, Abdi, where did you go to? It's okay. Jabet.
Okay, so allow me to have like a 1 minute conversation with Nemo. Like I have 6 balls, Nemo, and I want to pick like a subset of 6. Like say I want my data to be equal. So I want a subset of 6. So I've picked the 6 balls, then I have returned it again. I have picked again. I have returned it again. So that means, are they identical?
No.
Or
No.
They're not identical, they are random.
So that means there's a repeat. Like I can have one. Let's use colors. And red, green, blue. So there's one where I'll repeat. Like there's a subset where I'll repeat the colors, right?
Yes.
Then in that case, I am on your side now. I crossed over.
You see, I think the same thing that was confusing is the size. If we talk of the size of a data frame, the way Nemo has said, it's the data points, and the data points are always the rows. So if for example, my salary data has 20 rows, that means that when subset 1 comes to pick, it will pick the 20 rows. You see? Then it will return them. Like after picking it should be replaced back so that another subset should pick also. So yes, they'll be random, but they'll be identical. Actually, it will be unique for every model, but they'll be at some point identical because it's the same. It's the same data. So there's a possibility it's the same, but how it was picked. Maybe the red ball was picked first. So maybe on the first subset, maybe this row will appear the first one. But when you come to the last subset, maybe that row will be the end. But the goal here is that the size, like your subset size, should be the same as the original data. I think that's where I'm adding some sentiments. Yeah. Yes, Anthony? No, Jebet, you are not lost again. No. Okay, Anthony. Yes, Anthony.
Okay. Let's do something to make it easy for the person that asked the original question. Please go to that statement. Each subset should, just put your cursor in front of that should. So I want you to type something there. Yes, like want to edit it. Yes, put each of the should. It's just in front of the should. Like want to edit that statement. Should in front of the should there, in front of it. Be ready to type something. I want you to type something there. Go to the yes. So go to the should be in front of the BE, please. Yes, in front of the so just put from FROM. Type FROM from. Yes, I think that should help us in or help that person. So you can enter now. Don't go out of it now. So each subset should be from the same size as the original data, training data. Each subset should be from the same size as the original training data. That is, when each subset is speaking from the same size. Or if also you want to add to it that it's also the same size as the original training data, fine. But or we can say from and of the same size. Yeah, to be from and of the same size. So I think I don't know if what I'm saying helps. It should be from and of the same size as the original training data. Should be each subset should be from and of the same size as the original training data. Yes, exactly. I hope this helps or clarifies it better.
Yes, Anthony.
Yeah. So I think this captures what we're trying to explain. Each subset should be from and of the same size as the original training data. It captures the idea of picking with replacements, as well as each size. Each subset is the same as the original training data sets. So I don't know if that, but I'm sure of the from the same size. I'm not so sure of that. Of second adjustments. So bottom line,
The more you're talking, the more you're confusing yourself. But it's okay. It's okay. I've understood you, Anthony. I'm just cross-checking something. I think who addressed their hand? Yes, Lauren, just go ahead.
Yeah, I think I've understood now about it should be the same as the original training data set.
Mm-hmm.
So the difference comes in where, like, if the first subset I've picked maybe row 1, 2, 3, then the second subset maybe it has picked row 4, 5, 2, 1. So that I think the different arrangements. And if you remember when we were doing the random is equals to 42,
mm-hmm.
If another person doesn't use that random 42, you'll get different results. So I'm thinking in that perspective. So if you rearrange those rows, you'd get different results. I don't know if I've confused people even the more. So the difference is how the rows are arranged, but the size of the subset is the same as the original data.
Mm-hmm, mm-hmm, that makes sense. Mm-hmm. I think what I'll do, let me just share the Explore AI video. Let's watch it one more time. Then let's see how it goes. Just give me a minute so that I open just give me a minute. Mm-hmm. Because I know this is the one that is always it's always confusing. So let me just share again so that you can share. Can you see my screen?
Yes.
Okay, let's see. Let me just add the volume.
The same training data.
Oh, my volume is so low.
Helping to decorrelate each of the basic model units also helps to improve the variance of the overall model. Remember, variance is the error we find from bootstrap aggregating. We train some number of identical models on different subsets of the same training data, which, while helping to decorrelate each of the basic model units, also helps to improve the variance of the overall model. Remember, variance is the error we find from moving to another training set. These subsets are created by sampling with replacement from the training data set, so that should ring a bell. That's a process we covered before, which is known as bootstrapping. The resulting group of models trained on slightly different training data subsets is aggregated in order to obtain a final model prediction for our total ensemble model. In this instance, to aggregate is to take the mean or to take the average of the predictions from each of the individual basic models. So in a way similar to the voting process we looked at above. It's worth noting here that bagging is a stochastic process. Another way of saying that is it's a probabilistic process. This means that each time we carry out the bootstrapping step, the sampling with replacement step, where the sampling process is itself random, the training data for each model will differ ever so slightly, resulting in a different overall ensemble model each time. So whereas with bagging, many versions of the same model are trained in parallel and their results are aggregated to obtain one single prediction, in boosting, we train many versions.
Yeah. So I think we can agree that it should be the same size as the original training set. Are we good?
Yes.
I think that is because it's the set are coming from the training set. So they should be the same size as the training set. Yeah, I think we are now good. Unless there's somebody. Jebet, are you good? Are you okay? Have you got a bit, or you're still confused?
No, like if it's going to be like if there's some rows which are going to be repeated for different subsets, that's perfectly okay.
Yeah,
that's perfectly okay. That one I'll be okay with that.
Yeah, I think it's that way. It's that way. Because the subsets now are the one that will be, the subsets are the one that will create numerous like the subsets are creating, we'll have subsets that have, each subset will have a training data. I think that's what that person on Explorer has explained.
There's someone who has their hand up.
No, it's Anthony. I think he didn't. Yeah. Anthony, do you still want to talk? I think it's a mistake because he had already.
No. Thank you. I'm good.
Yes. PG, are you okay? I'm checking on those people who are confused. PG is okay. Jebet is okay. Nemo?
Wait, Jebet, you said if the rows are being repeated or something, like there'll be duplicate rows in the data, Amma, what did you say?
No, like in every subset, let's say subset 1, it has index, like there's some, how do I explain this? Like there's some
just use balls. You can say green, blue, yellow, and then
there's some balls which will have green, red, yellow.
Mm-hmm.
Yes. Then there's one which will have red, green, blue, green, like some which will not be repeated, and there's something like that.
That means you'll have duplicate rows in some, when you're talking about a data frame, you'll have duplicate rows, and sometimes
it
could be unique.
Yeah.
I am not sure everyone has gotten that part that you're talking about.
The silence is loud.
I don't want to push this too far.
The silence is
We'll
loud.
do more research. Let's go. Let's keep going.
We'll do more research on that.
Okay. So I think even the way they've explained on Explorer is even easier. So after that, now these ones will be the ones that will have the training data, like this subset. So the subset 1 will have the training data, subset 2 will have a training data, then subset 3 will have a training data. Then from there now we have a base model training, independently train each base model on the bootstrap subset of training data, fitting the base model to the subset of data and deriving the model parameters or weights in what it entails. Then combination of prediction model. Once all of the base models have been trained, they may be utilized to make predictions on the test set. To create the final prediction, the prediction of the base models can be integrated using voting or averaging approach. The most popular strategy for classification issues to employ majority voting, in which the class with the most votes from the base models is chosen as the final prediction. The prediction for regression issues can be averaged to give the final forecast. Then evaluation performance, I think there we are looking at RMSE. Then for further optimization, we can fine tune. So I think this is an easy, like broken down. So you divide the data into training and testing. Randomly choose some samples from training data with replacement to create subsets. Then choose a machine learning algorithm such as decision trees, random forest, or neural networks. Then train multiple instances of chosen model on different subsets of the training. Then using bagging Ensemble to make predictions on the testing data by aggregating the predictions of all models. Then you can evaluate your model. Yes, there's a hand. Is there a hand?
No.
Okay. So I think we are good. Are you people good? Okay. You'll go and repeat, and you can also go and watch more YouTube videos. You can also go through my article because I explain it differently and did want to explain it that way. because there was using M numbers, N numbers, so I didn't want to confuse both of you. Yeah. So let's go ahead. So the same thing happens. So we come and import the bagging regressor. Then we instantiate it. So we give it a maximum depth of 4 because we instantiate a decision tree to be used as a base model. A person can use you can decide to use any model, even the linear regression or the random forest. So this one is the one that will be reading from the base models. This base model is the one that will be reading the training from the subsets actually. Then now you come and instantiate the bagging regressor and you give it an estimate as the decision tree. Then you fit it. After fitting it, you repeat the same procedure to check out the RMSE. And here we are getting 0.31, which is not very good as compared to the homogeneous ones that we've been doing. So that is it. Yeah. So that's for bagging. Are you good? Or are people confused? I think we are now good. Yeah. So let's finish the last one and call it a day. So the last one is boosting. So boosting is also an example of homogeneous. So for boosting and ensembles are built by combining multiple weak models. For example, a decision tree with a depth of 1 in a sequential fashion. Each model is built from the previous model training set. This training set is selected through weighted sampling with replacement where the weights are the previous model prediction errors, for example, residuals or individual training samples. We'll illustrate that more, don't worry. The final predictions are then made by aggregating the individual predictions of all the models in the ensemble. So boosting involves successfully training models so that each one tries to fix the mistake of the one before it. Predictions are derived from the weighted sum of models, which are ranked according to how accurate they are. Other boost, grounded boosting, and XG boost are few examples of boosting. Yeah. So the sample is used. Boosting involves sequentially training weak learners. Here, each subsequent learners improves the errors of previous learners in a sequence. A sample of data is first taken from the initial data set. This sample is used to train the first model, and the model makes its prediction. The samples can either be correctly or incorrectly predicted. The samples that are wrongly predicted are reused for training in the next model. In this way, subsequent models can be improved on the errors of the previous models. Unlike bagging, which aggregate prediction results at the end, boosting aggregates the results at each step. They are aggregated using weighted averaging. Using weighted averaging, each model is assigned a simple weight based on how well it predicts the future. Stated differently, it assigns greater weight to the model possessing the higher predictive power. This is due to the fact that the learner deemed most significant is the one with the most predictive power. So I think this one we'll need something like, how is it called? We'll need that thing. How will I write it? Or we can just
Jamboard, Anna.
Yes, but we can still explain using this, right? Or we do it on Jamboard so that it becomes easier, because it's the last one. I don't know. I don't remember where I was getting it. Yeah, I've gotten it. I hope you people are good. Yes, that's true, PG. Very much correct. So I think I just allow anyone to be an editor so that maybe if somebody wants to draw, they can just draw. So I have to reshare my screen. Yeah, I think everybody can edit on it. So if there is a confusion, just make sure you help each other so that you can do it. So with boosting, a boosting model is built by combine multiple weak models. For example, a weak model might be a decision tree, and you do it in a sequential manner, one after the other. So for example, I think if we have here something like our training data, you see, so you have model 1, you have model 2, and let's say you have all the way to model K. So these are the models. So I think this will be our first, which you'll make predictions on it. So you build a model from the training data. So the first model will go first. So after going, it will give a prediction. I don't know if you're getting it. So after giving a prediction, you'll realize that maybe it will not give the best prediction. We'll have some residuals that it will not have solved. So those residuals are the ones that are picked. Then the next model goes. Like now the second one. And again, it does the same thing. It predicts. Then again, it picks those errors and goes now to the next. Until when now it will come and give us now the final output by looking at the weight of each of the how each of the how is it called? How each of the models were performing. So I think that is all about boosting, if I'm not wrong. So let me stop sharing. I think that is easier. So I think I can stop sharing, then I come back to present now the even I've realized I wrote my title on. I've shared the wrong one. This one is the one that we were doing yesterday. Sorry guys. It's this one. I wrote the wrong title. I wrote Ensemble practice. Just realized now. So you can see that is what is happening. So you train, it goes, maybe it gives a false prediction because of the errors. So this one picks from there. Then again it goes. Then like that until you'll have now an overall prediction. So you still do the same thing. You import the package Ada Boost Regressor. Then you pick a boss model. Here it's the decision tree regressor. Then you give it a maximum depth. Then you give it an estimator. You train it. Then now you go ahead and calculate. Like you calculate the RMSE and all of the sorts. Yeah. So I don't know if somebody has a question there, or if you can add something before we go. So the goal is that every subsequent learner, like the subset, the model, every subsequent model that is coming, it improves the errors from the previous one. So it improves those errors that were gotten from the first base model, from the first model. So it goes ahead like that, and again the next one also do that. So it just corrects what was not correctly, because there's a model that can predict incorrectly and there's a one that can predict incorrectly. So those ones that are predict incorrectly or wrongly are always reused for training now our next model, so that the subsequent model after that one improves the errors of the previous one. Then after that, now you aggregate the predictions in the end by getting now the aggregated weight, the aggregated weight averaging. Yeah, I think that one is straightforward. Yeah. So any question? I think these are advantages and disadvantages. You just go through them, but I'm done. I'm done and closed, unless somebody has a question.
Thank you.
You're welcome, PG. And thank you, guys. Yes, thank you, guys. Thank you, guys, so much. I hope you've understood. But the more you'll practice, the more you'll be familiar with them, because while training your models, you'll be reaching somewhere you'll not be getting good prediction. So that means you'll have to change your path to go and use another thing. So the more you become familiar with them, the more it becomes easier. Yeah. Thank you so much, guys. So I think I'll give it back to Eve, or we finish with the argument of yesterday for something like 5 minutes. Then we give it to Eve. Then you call it a day. Then don't forget to read my article and give me a thumbs up.
Hello, Linda.
Yes, Ijoma.
Yeah, thank you so much for today's section, first of all.
You're welcome.
Before we go into the argument for today, I asked question yesterday, but I didn't get clarity. And I still went back to, research kind of, and I still was not satisfied with trying to balance the argument we had yesterday regarding purity and homogeneity, because you guys said it's the same, and I want to understand in the consent, or is it like I really need to understand that honestly. Yeah, because there was something that Javette explained yesterday, and she used colors which were clear. Like, okay, so this is determined by the purity. So the thicker the color is, the less purified. Kind of, let's even use that word, if there's something like that, right? So and the more thick the color is, the less accurate. Let's even say that. So I want to understand in the context where homogeneity is same with purity. I don't know if the question is clear.
Yes, I think the reason why I said that is because if you talk about homogeneity in a decision tree, you are looking at how the degree of similarity or uniformity within the set of points in a node are. You see? So like for homogeneity on my side, you see like you have data points at the node. So like the more maybe the darker color is or something of the sort. So you see every node has 8 different data points. So that means if there is homogeneity, that means that between those data points, there was a higher degree of similarity and uniformity between those data points that belong to the same class. So maybe a node was giving you X, a threshold of X is less or equals to 5 like yesterday. So there are some data points that will be there. So those data points have some degree of similarity and uniformity because they are in the same class of that threshold. And that's why they are picked in the decision tree to be there. You see? Then for purity, I think it's something like, because I've had purity, especially when doing something like entropy and Gini impurity, of which we've not learned about that. But I think mostly it measures the dominance, like how dominant the data points of the majority class are in a node. So that's why I went up ahead and said at some point, it's not like it's the same thing, but I remember saying, Jebet is using purity to explain that, but for me, I used homogeneity to explain it because it's giving out, at the end of the day, it's giving out the same information of what was happening on the decision tree. Yeah, so that's what I meant. So if I confused anything, I think we can clear that right now. Yes, Abdi?
Yes, I think all of you guys mean the same because what the algorithm that the tree uses to actually determine the optimal split point is the impurity criterion, which basically measures the heterogeneity or the heterogeneous, which is basically the uncertainty in the data set. So when you say purity and homogeneous, the same, impurity and heterogeneous, the same. So I think it's the same criterion that the algorithm uses to actually chooses to take the split, potential split points. Yeah, I think yesterday maybe you can put your screen up, Linda, and then maybe I had a question, not per se a question, maybe a clarity that how the algorithm how gets to the, for example, we had years of experience, and our decision tree began with the base root was actually, or the root node was I think something like less than 5.5. Yeah, the year of experience being less than 5.5. Okay, so maybe you can just or Jebet or even you can talk about how we got to that point, that how the decision tree, how the algorithm chose that 5.5. I think that will give clarity in the maybe arguments we were having yesterday, probably.
Yeah, that's true. I think Jebet, you can share your screen because of what we discussed during the day, right? Are you ready?
Okay, I'm not ready, like me, I can share.
Okay, thank you.
give me a minute. I search for that notebook again.
No problem. It's called decision tree.
I don't know if I have it opened.
Because the changes we made with you, I don't have them on my side. I didn't make them on my side.
You didn't even make changes.
Yes, we did something.
We just experimented.
Yes, that's what I'm saying.
And I reverted it back to normal.
You did that?
Yeah.
Oh, now that's not good.
But we can still do it.
We can do it again, actually. Yeah.
It's going to a decision tree?
Yes. It's called decision trees practice. Practice.
Okay, I have so many folders. Takes a minute to. I have found it. I'm coming. You guys can see my screen?
Yes, we can.
So, Abdi, what were you asking?
Yes, you can get to where was the sheet?
I think change the depth to B2 the way it was.
Yes, change the depth. Yes, Debet. My question was just maybe to ease on the conversation we had yesterday. You see the first we have the first split there, which is the root node, isn't it?
Yes.
How did the algorithm chose that 5.5? Maybe
it looks at all possible values for that point, calculates their mean RMSE and then the minimum. So 5.5 was giving the minimum. That's why it was selected.
Not sure.
Please, can you say that again?
You see, how does a decision tree decide this split based on the minimum RMSE? So it considers all possible values, like maybe 5.3, 6, 1, and then 5.5 was the one that had the minimum RMSE. Then it was selected. I don't know if you get me.
Okay, from the way I've understood, it's a bit different from the way I've understood. Maybe to add on that, is that, for example, here we're talking about the feature variables, isn't it? This case right now we're discussing is the years of experience, which is our access. So what happens is probably the first time it will consider every unique value, and then it will evaluate potential split point between, for example, let's say we have years of experience. We have it was starting from 1.1, then 1.3, 1.5. Maybe you can check the head of, you can just check data or head, and then we see how the data looks like.
It's actually not a big data, so.
Yeah. So we see here we have 1.1, 1.3, 1.5. So it first, between 1.1 and 1.3, that two forms a potential split point. So what the algorithm does, it automatically picks a point in between, for example, 1.1 and 1.8. Then it divides that data specifically into two subsets. And then one subset where probably, for example, if it has picked 1.125, then that becomes our split point. Then the subset is actually the data is divided into two subsets. We have our split point. Then one subset where now the feature value is less than or equal to the split point, which is 1.125, and another subset where the feature value is greater than the split point, which is 1.125. Then for each subset, the algorithm will calculate the mean target value for that. The mean target value, that is the Y. That's in this case, we're talking about the age, the salary. And then it uses that to calculate the mean values. So it uses these mean values to calculate the MSC. So that specifically, we have an MSC for that. Now for the left side, we will have the two data sets. For the left subset, we'll have an MSC, and then the other one will have an MSC. So that's specifically it for each potential point. So we'll have many potential points. So we have one between 1.1 and 1.3. That forms a potential split point. We have chosen a randomly, and then between 1.3 and then 1.5, that's another potential split point. So it actually calculates the the MSC for each potential split point. So the algorithm, what it does, it will evaluate the decrease in MSC, resolving for each split point. So for each split. Then from there now, the decrease in MSC is actually what it's going to use to actually come up with 1. That specifically right now we're seeing 5.5. I don't know if I've explained very well, but that is the logic behind how the algorithm comes up with this 5.5 and then 2.25. The rest is just recursive splitting. So that's how I thought it came up, and from my understanding actually and my research.
Yes, I think you've just explained what I wanted to explain, maybe in better words.
Okay. Yeah, that's what I was saying yesterday. It's easy to understand, but explaining kind of makes it very difficult.
That's true.
Yeah, from there now, the assumption you've made of actually wanting to determine the salary for a person who has a 5-year experience, it's easier. The way you've explained was actually correct from there. Yeah. But the value you've chosen, for example, if you go down there, you said the value for a person with 5 years experience. No. So now you can go to the leaf node, the last one. Yeah, for a person with 5 years experience, I think we went up to the value being 59,047.444, isn't it?
Yeah.
So yeah, something like that. So that means even for a person who is like 6 years experience, a person who's like 5.5 years experience will still get the same value. So this is the predicted value for that specific. So it falls within the category of the leaf node. Yeah. So it's a bracket. It's not specifically the Y value for 5 years experience. It's just a category, I think, for that years of experience. It's less than 2.55. That was how I thought.
So basically, all the values that will be like less than 5.5 and more than 2.55
yes.
will fall under this category.
Exactly, yes.
It's just like that. Like
yes.
Explain slowly now.
Linda, maybe you can do that. What's your question, Nemo?
I've left you where I selected 5.5 is the lowest. We had the lowest MSC. That's where I've understood that there. Now go slowly.
Like now, basically.
Actually, 5.5 even did have the lowest MSC. If you look at it, it did have the lowest MSC.
Mm-hmm. So how was it selected?
That means that if our end node where debate is the way Kadira said, it's predicting the values that below 5.5. Is it below 5.5 and also below 2.5 if I think so? So that is the predicted. It's not the predicted value of. Is it because if you pick 5, of course it will give you that. Even if you pick, I think if you pick also 4, you'll lie on that leaf node, right?
Yeah, anything between 2.55 and 5.5.
Yeah, so that's what we are saying. Have you gotten it, Nemo?
I think I understand.
Yes, explain again. Explain it again.
What Nemo is saying. You see, before this, like when the model was being selected, according to what Abdi has said, when the model was being built, there was so many other potential splitting point. It wasn't only 5.5. Like it was possible to choose 1.5. It was possible to choose 2.5. It was possible to choose 9.5. But the model came up with 5.5 because it was the one that had the minimum MSC.
So that means even if you use 5.4, you'll still end on that leaf node, right?
Among all the potential splitting points. So, like according to this, like the whatever we provided the model, like this max depth of 2 and the random state of 42, this is the best model that it could come up with.
Yes, maybe I can explain to Nemo.
Yeah.
If you go to that table, maybe from the table, here, and Nemo, normally the way the algorithm does it, it's actually, see, we have years of experience. We have 1.1, we have 1.3. So normally it will just check the unique values, and like for example, with unique values, that I mean, like for example, we have 1.1 and 1.3, and they have to be adjacent to each other. So it will take between 1.1 and 1.3. It will just maybe take that as a potential split point, and then in between it picks any random value. For example, it can pick 1.125, 1.13. So once it does that, so at each, let's say we have a split point at 1.125. Now at each potential split point, now the algorithm, it will divide that data. This is 1.1 and 1.3 into two subsets now. So one will be where we will have the feature value, it's less than or equal to the split point, which is 1.12, and then we will have on the other side, on the right hand side, the feature value will be greater than the split point, which is 1.13. Now it will actually compute for each subset. Now the algorithm will calculate the mean value, the mean value, which is now the mean target value for that, and then from that mean target value, it will compute the MSC of that subset. For example, if you are on the left hand side, which is where we say the variable, the feature variable is less than the split point, it will compute for that MSC, and then it will do the same for the right hand side. And then once it does that, it will check between the two, and then the algorithm will evaluate the decrease in MSC. That one split. Now if you go to the second split between 1.3 and 1.5, there's another potential split there. Between 1.5 and 2, there's another potential split. Between 2.0 and 2.2, there's another potential split. So like that. So it will compute a lot of MSCs, and now the list, it normally aims for the split. It will aim to select the split with the split point that actually maximizes the decrease in MSC. So that's how actually we go to that 5.5. So it's a wonderful thing that's doing actually behind the curtains, that we know we don't appreciate much. So that's how it actually picked the 5.5, and that's
so it just picked some numbers from this list. It just picked like where there's a potential split and just showed us a decision tree.
Yes,
that's
from
what
there.
you're saying. From there, it went and took like let's say a particular data points, the lowest MSC, and then it did a decision tree so that we can understand how to predict. That's what you're saying.
Not sure I have understood that what you said, but maybe you can instead of saying decision tree, you can use nodes. That would be easier.
What I am saying is, you see, you've said between 1.1 and 1.3 there's a potential split, isn't it? So the model will pick any value between 1.1 and 1.3 and then evaluate the MSC. That's what you said, or I've understood it wrongly.
Now, when it does So to make it clear, when it picks a potential point, it will still divide into two subsets. Okay. So two subsets. We are still within 1.1 and 1.3. So if it has picked, let's say, a split point of 1.125, that is the split point. It actually, the algorithm will divide that data into two subsets, whereby we have we are talking about our feature value, which is now the age, the years of experience. We will say now years of experience is less than, that's one subset, less than or equal to the split point 1.125. That's on the left-hand side. And then on the right-hand side, we're saying the feature value, which is now the age, the years of experience, is greater than or equal to what? To the 1.125. That itself now, now for each subset, again, you go to the left-hand side, the algorithm will calculate the mean target value, that is for the Y, the mean target value for that. And then on the right-hand side, to do the same. Then for each of them, it will calculate the MSC, and then it will compare that MSC. Now that's for one case. Now it goes to the next 1.3 and 1.5. That's the same. 1.5, so it's a lot of work. So it's computing out 1.5 and 2.0. So that those now it will actually aim to select the split point that maximizes the decrease in MSC. Slight smallest. Okay, when we say maximize the decrease, it's quite kind of used to confuse me basically. For those who know English better, yeah. So anyway, I think
we've understood. Yeah, I've understood. Thank you so much.
Yeah.
So anyone who still needs any clarification or has a question on this?
So, Jabet.
Yes.
Okay, so we're just confirming that yesterday when we got 59,047 for 5 as our predictor was correct.
Yes.
Okay.